going to look at another example, several examples of comparison test of infinite series. So here are the problems. Number 3a, determine if the series summation from 2 to infinity natural log of n over n converges or diverges. Now we could use the integral test here to determine convergence or divergence, but this example, in this video, we're going to see how to use the comparison test. Problem part B, determine if the series summation from, again, 2 to infinity, because if we plug in 1, we just get a 0. So 2 to infinity, ln of n over n to the 5th power converges or diverges. Likewise, we can use the integral test also here. And then part C, determine if the series summation from 2 to infinity one divided by n squared times natural log of n converges or diverges. So all three of these examples we're going to utilize, you're going to use comparison tests. So let's recall what a comparison test is before we go ahead and solve the three examples. So here's the setup for comparison tests. Suppose that the series, it doesn't matter where it starts as long as it's defined. Series n equals 1 to infinity a sub n, and another series n equals 1 to infinity b sub n are both positive term series. And that means a sub n and b sub n are positive. It could be starting in 1, but if they, for example, they start being positive at 100th term, and then stay positive, that's okay too. So both, we're going to assume all the terms are positive, and part 1 of comparison test goes like this. If the series b sub n from 1 to infinity converges, and then term by term a sub n is smaller than b sub n, then the a sub n series also converges. And then the second part of the comparison test is, again, if b sub n series, this time, if it diverges, and the a sub n a sub n is bigger than b sub n for all n, then the a sub n series will likewise diverge. And before we again go on to solve the three examples, we want to learn about inequalities involving the log. So natural log of x is always below x and bigger or equal to 1 for x greater than or equal to e. So starting at e, natural log of e is 1, and then it gets bigger after that, but it can never be as big as the x that you input into it. So if we restrict our input to positive integers, we have this nice inequality for the log. ln of n is bigger than 1 and smaller than n. So ln of n is bigger than 1 and smaller than n for n greater than or equal to 3. And so now we can now start with example 2a. We want to determine if the series n equals 2 to infinity ln of n over n converges or diverges by using the comparison test. So what we're going to do is use the left inequality for the log. So even the series starts at 2 and the inequality kicks in at 3, it really is irrelevant. So we have 1 is less than ln of n. We divide both sides by n. We have this inequality 1 over n is smaller than ln of n over n for n greater or equal to 3. So we'll call 1 over n b sub n. We'll call ln of n over n a sub n. And then the 1 over n series, we know that that series, the a sub n series, or the b sub n series, diverges. It is the harmonic series, or you can use the integral test. So here we have the b sub n series, which is 1 over n, it diverges. And the a sub n series is larger for each n, starting at 3, larger than b sub n. And that means when we sum them up, the a sub n series will be bigger than the b sub n series, but the b sub n series is already infinity. Therefore, the a sub n series must diverge. So here's the conclusion. The summation from 2 to infinity of b sub n, which is the summation from 2 to infinity of 1 over n, this series already infinity diverges, is smaller than the series summation from 2 to infinity ln of n over n, which is the summation n equals 2 to infinity of a sub n. And by the second part of a comparison test, since the b sub n series diverges here, the a sub n series must also diverge. So the series 2 to infinity ln of n over n diverges by comparison test. So here is problem 2, example 2b. This time we're looking at the series, the summation from 2 to infinity. And this one is natural log of n over n to the 5th. So here we want to use the right inequality of natural log, namely natural log of n is less than n. And this one really starts at even at like a 2. This is for all n greater or equal to 2. So natural log of n is smaller than n. Now we're going to divide both sides by n to the 5th. That makes natural log of n over n to the 5th is smaller than n over n to the 5th, which is 1 over n to the 4th. We're going to call ln of n over n to the 5th the a sub n sequence, and then 1 over n to the 4th, or n over n to the 5th, the b sub n sequence. Now we're going to look at the b sub n sequence here. So the sequence from 2 to infinity of b sub n, which in simplified form is summation from 2 to infinity 1 over n to the 4. We know that this is a p series with p equals to 4. Since that's bigger than 1, it converges. So the b sub n series converges, and the reason you can cite is it's a p series with p equal to 4, which is bigger than 1. or you can also show this by the integral test. So then we have the following. We have the summation from 2 to infinity a sub n, which is equal to summation from 2 to infinity ln of n divided by n to the fifth power. Is, of course, all the terms are positive, so this sum is bigger than 0, but it's bounded above by summation from 2 to infinity of 1 over n to the fourth, which happens to be our b sub n series, summation from 2 to infinity b sub n. And since we already established that b sub n converges and a sub n is smaller, that means the conclusion is that the a sub n series, which is summation from 2 to infinity natural log of n over n to the fifth, converges, and it converges by the comparison test, direct comparison test. Okay, now let's take a look at the last part, number 2c. Here we want to determine if the series from summation from 2 to infinity 1 over n squared times ln of n converges or diverges. So we want to use some kind of a log inequality, either the right or the left. Let's take a look. So we'll start with ln of n. It's bigger than 1. We'll start with the left inequality. This is true for all n greater or equal to 3, which is perfectly okay. Now let's multiply both sides by n squared. N squared alone is less than n squared times ln of n for n greater or equal to 3. Now let's flip these. 1 over n squared is greater than 1 over n squared ln of n. This is for all n, and that's positive for all n greater or equal to 3. 1 over n squared is b sub n. 1 over n squared ln of n is a sub n. You can see that b sub n is bigger than a sub n, but let's look at the convergence or divergence of b sub n. It's easy to establish. We already know what it is. So the summation 1 to infinity 1 over n squared, we know this series converges. That is the b sub n series. We know it converges. Again, the reason is it is a p series with p equals to 2, which is bigger than 1, or you can establish its convergence by using the integral test, and that would also do it. So we know that the b sub n series converges. A sub n sequence terms are smaller than b sub n, therefore by comparison test, the a sub n series, here's the inequality that we have. Here's the a sub n series is positive. It's 1 over n squared ln of n. It's smaller than the converging series 1 over n squared, which is the b sub n series. And therefore, you don't have to write all this out, but this sort of takes it step by step back to the definition of comparison, what comparison test is. And therefore, we have established that the a sub n series is smaller than a converging series, which means it must converge. Hence, summation from 2 to infinity 1 divide a sub n, which is summation from 2 to infinity 1 divided by n squared ln of n converges, again, by direct comparison test or term comparison test or just comparison test.